So now let's look at the selective search algorithm. So this is where we are implementing the selective search algorithm. As said, we are implementing a selective search algorithm, which is there is an implementation from OpenCV. So we are using that to find the regions of proposals. So here this is the class which is being used, and this is for the selective search algorithm. So now what we are doing is um, we are fitting this image, or we are just giving this image as the input to the selective search algorithms, and then what we get out of it is these objects called the rectangles. Now these rectangles, the recs or the rectangles are those bounding boxes for some regions or some proposal regions which the algorithm thinks that there is some object or the other in that region. So it doesn't mean that there is a pothole or the object which we want to do, which we want to detect. All it says is there is some object there with some probabilities, and that's what we get from these rectangles. Now once we run this, let's look at how many rectangles we have got. We've got around 915 different rectangles. That means there are 915 different objects, or different objects have been detected. It's not different objects, 950 instances of objects have been detected by the selective search algorithm. Now what we need to do is we need to now, based on the bounding boxes which has been output from the selective search algorithm, we need to look at we need to crop the image based on those bounding boxes, and then we will use that data to predict whether what is that object about, and predict whether there is a pothole in any of these objects. So that's what we are going to do next. So as a start of it, we define or initialize two different empty boxes, one for the proposals and one for the bounding boxes, and then we iterate through each of these rectangles which we got. So the different different data points related to it are the x, y, and the width and the height. These are the elements within these rectangles. So having got these elements, the x coordinates, y coordinates, and the width and the height, we crop the image based on that. So this is from y to y plus h. So what we get is, this is a y coordinate, and then the height of it, that difference, that is it. Similar with x coordinate, and then the width of it. So that's what we got. So we crop those images, and then we and then we change it into from now OpenCV. What happens is OpenCV always gives in the channels in the order BGR. It's the reverse of the RGB. So here we're going to convert it back from the BGR order to the RGB order, because we need that for our predictions. And then we resize it to our standard size, which is 224 into 224. And then the other steps which we have already seen during the training process, we convert that into array, and then pre-process it, and which is we normalize it, normalize those pixels, and then append that the arrays, which are those proposal regions, or which is the data which we appended to the proposals, and the boxes, the coordinates which we got from the rectangles, we appended in the list called the boxes, right? And then let's see. So next is the prediction process. Now we have got the data, which is your array, which is that form which is used for our inference cycle. So now we convert that into an array, because this was earlier one was a list. We convert into an array, and boxes also we convert into an array. Okay. And then what we do is we predict with the model which we've got, which we had trained. So this probability gives you the class probabilities based on the. So this proposals are our arrays which we've got. Okay, the arrays of the images which we've got, and we get a probability from this. And so this is the shape of our our proposals. We have got 915 instances, and this is the array sizes, right? And probabilities would be just the probabilities of each of those 15 different objects which we've got. Now to get the labels, what we do is as usual, we take the argmax, or the maximum probability. So that's because that's the predictions, because as you remember, when we get the probabilities, you have two probabilities. One is of the positive and the negative. In let's say the negative class is 0.35 and obviously the positive class would be 0.65. So we need when we take the argmax, we'll take the 0.65 because that's the maximum, and the index is 1. So then that means the predicted class is the positive class, which is the second index, right? So that's why we use NP argmax, and then we take that label of it. So when we LB classes gives the name of those classes, and what we're doing is we are taking the IDs of where the potholes are found, because all what we are interested is in identifying the potholes, and then so therefore we find only those IDs where the labels are 1, because 0 is not a pothole and 1 is a pothole. So that's why we are giving this. So this is the list. These are the list of the IDs which we've got. So this means these are those these are those instances, and out of those 915 instances where there is a likelihood of a pothole. So we don't know what probability it is. That we'll come to next. But these are the elements, or these are those instances where a pothole is likely to be there. So once we get those IDs where it has been predicted as potholes, then what we do is we get the boxes also. From the complete list of 915 boxes, we get only those boxes where it pertains to the potholes, and we also get the probabilities for those for those potholes. Why are we getting these probabilities? Because we'll see in the next step, that is, we will take only those objects where it's where the probability of prediction is greater than a threshold. Say for example, we define that only if the probability is greater than, say, 99%, then only then we accept it as a pothole or the object which we want. So that's why we are getting the probabilities. So we'll come to that specific step next. So here, this is what I've been talking about. So first we print the length of the boxes. Now out of the 915, 845 of them have been predicted as potholes. That's these numbers here, and then we are defining a threshold. So we are defining a very high threshold, because most of the predictions have a lot of are greater than 90%. So we're predicting a very high threshold. Now how do you arrive at this threshold value? It's only after looking at some of those sample probabilities we'll be able to define a threshold. So I've looked into those probabilities. So if you just print out these probabilities, you will find let's do that. Let's just print the probabilities. So here, so this is what we are talking about. So see, 99.639999. So these are the kind of probabilities which we have. Okay, so here we have taken only the the first ones. If you note that we are taking only the probabilities of the potholes, and we have excluded the other ones. So you can see the values here. So that is the basis on which the threshold was arrived at. Okay, so after we define the threshold, we say that we pick only those IDs where the probability is greater than the threshold probability. Okay, so again we get another filtered set of IDs, and we take the boxes and the probabilities of those again the further filtered IDs again. So originally we had 845 predictions or instances where where it was predicted as a pothole, and now after filtering, after applying the threshold, we've got only around 395. So that's what we're saying. So now let's see how good these predictions are. Whether the predictions are they kind of are they really potholes or something else? So that's what we're going to test. So we are taking a copy of the image, and then we are iterating through the boxes and the probabilities. Okay, so boxes gives you the coordinates of the bounding boxes, and the probability gives you your how probable this the probability that this is a pothole. So you take the coordinates, the start x, start y, and end x, end y of this, and then we draw a rectangle using these coordinates, the x and y coordinates, starting at x and y coordinates and ending x and y coordinates. That's what is done here. And then we are also, what we're doing is we are also giving a coordinate for where to write our class name. So our class name is probability in a potholes, and so we are defining a kind of a coordinate where we could write these write the text which we want, which is pothole. So here we are defining what is the text, and we are also defining when we give the bounding boxes, we are displaying the probability and the text, which is the class name. So that's what. And finally we are putting the text on the image, and then finally displaying this thing. So this is what we got. So we have seen that there are around, so you can see there's a lot of bounding boxes here, and you can be happy that most of these bounding boxes are kind of aggregating around the regions where there was this potholes. So in a way, our algorithm is actually working, or our training has worked, and it is actually aggregating around the regions where there is a pothole. Now, as you know from the earlier steps, the next step is to reduce this number of boxes, and that's where we'll be using the non-maxima suppression. So that's what we will see next.